The second question asked, what is the effective spring constant of the bungee cord? Again, spring constant is a number that describes the stiffness or the stretchiness of a spring. It's measured in newtons per meter. I've noted some important values that we determined in step 1. We found that the speed at position 2 is 14.0 meters per second. That was the answer to the first question. I also jotted down the total gravitational potential energy at position 1. That was 62,475 joules. Again, we're assuming that that total energy is conserved to position 2 and position 3. Our next question has to do with the elastic potential energy, because we're trying to solve for the effective spring constant of the bungee cord. I know that the total energy down here should also be 62,475 joules, but it's split between gravitational potential energy and elastic potential energy. There's no kinetic energy at this point because the stretched bungee cord has brought the bungee jumper to rest. So let's set up an equation. I know that the total energy should be 62,475 joules. That should equal the gravitational potential energy at the bottom in position 3 plus the elastic potential energy. Let's plug in the equations for those two energy forms. Again, the total is 62,475 joules. The formula for gravitational potential energy is mgh, and this would now be at height 3, 5 meters above the ground. The formula for elastic potential energy is 1/2 k x squared. K is the spring constant, and x is the amount of stretch or compression in our spring. This is a bungee cord, so it can only be stretched. So we're looking for the amount of stretch at position 3. Let's start plugging in some numbers. The mass of the bungee jumper is 85 kilograms. The value of g is 9.8 meters per second. And the height at position 3 is only 5 meters above the water. And then we add in the energy stored in the stretched bungee cord. 1/2. K is our unknown, and x is the stretch of the bungee cord. We had figured out that that bungee cord would stretch 60 meters from its unstretched position if the bungee jumper reached a height of 5 meters. We do need to remember that that term is squared. Let's work out the values on the next line. The gravitational potential energy at position 3, when I multiply these numbers together, is 4,165 joules. There's not much gravitational potential energy here because the bungee jumper is only 5 meters from the water. If I take 1/2 times 60 meters squared, I get 1,800 meters squared times our unknown spring constant K. So I need to subtract 4,165 joules from both sides of the equation. This goes to 0. And we're left with 58,310 joules on this side of the equation. I'm going to write joules as Newton meters here, and you'll see why in a moment. Finally, I need to solve for K. I divide both sides by 1,800 meters squared. So we will have solved for K. 58,310 divided by 1,800 is 32.4. Let's consider the units. I've got Newton meters divided by meters squared. I could think of that as meters times meters in the denominator. And meters will cancel here. So I end up with units of newtons per meter. And that is the standard unit for spring constant. Again, the spring constant describes how many newtons of force you get for every meter of stretch of the bungee cord. So that's our answer to the second question. The final question asks, if 3,675 joules of the total starting energy dissipates, what height will the bungee jumper reach when she rebounds upward? Assume the cord becomes unstretched. What we're considering here is what height the bungee jumper will reach. We're going to assume she's going to end up somewhere in here between the unstretched height and the beginning height. Energy would be dissipated in a case like this because there's air resistance, there's stretching of an object. all of those things could potentially cause a thermal energy increase. If there was no energy dissipated, the bungee jumper would actually reach a height of 75 meters on the way back up. Let's consider a fourth energy pie chart to organize our thinking on this problem. It would be somewhere in here. When the bungee jumper reaches her highest point on the rebound, she would be at rest, so there wouldn't be any kinetic energy. The cord is also unstretched, so there's no elastic potential energy. There would be a large portion of gravitational potential energy, as well as the dissipated energy total that the problem gave us. The energy pie chart would look like this. There's a wedge of dissipated energy, I'll call it E subscript dis, as well as a large amount of gravitational potential energy. Because some energy dissipated, the bungee jumper will not reach the same height or gravitational potential energy total as she started with, but we still expect the total energy to be 62,475 joules. So I'm again equating the energy total at the top to some other energy total. Maybe we'll call this position 4. So the energy total is the same, 62,475 joules. That includes the dissipated energy total given in the problem, 3,645 joules, plus the gravitational potential energy at position 4. That's mgh4. Let's plug in values on the next line. The mass, 85 kilograms, times g, 9.8 meters per second, times height 4. Let's go ahead and subtract 3,645 joules from each side of the equation. This cancels to 0. We're left with 58,800 joules on the left-hand side of the equation, and the remaining term that represents the gravitational potential energy at height 4. 85 times 9.8 is 833. For my unit, I'm multiplying kilograms times meters per second squared. You might remember that that is the definition of a Newton, so I'm going to change the unit to a Newton. That value is multiplied by h4. My last step, I'm going to divide by 833 newtons on both sides. Remember that a joule is defined as a Newton meter. So when I divide this number out, newtons will cancel, and I will end up with a height in meters, just as I expected. When I divide 58,800 Newton meters by 833 newtons, height 4 equals 70.6 meters. And that's our final answer in the problem. It's probably a good thing that there was some energy dissipated. Otherwise, the bungee jumper could be injured when she bounces back to the original height. Hopefully that problem gives you some strategies for approaching energy conservation problems that involve elastic or spring potential energy. If you have any questions, please post them in the comments. If this video helped you, please consider subscribing to my channel as well. Thanks for watching.